And today we're going to have our November seminar from the UAB chapter of Sigma Xi. Wow, technical difficulties. Just to start with, let's see if we can do that. So we always start with our November business meeting. So thank you for your membership too. And remember, if you need help, renewing or becoming a member, just email us at sigmaxi@uab@gmail.com and we can help you. We just had, right, the last week, our annual meeting. That was very successful. We'll continue with the seminar series for the spring, and I'll be talking to you guys next in January. So it'll be the third Wednesday of the month. And we want you to stay connected with us, right? So we send announcements for people that have attended our seminars in person, that want to be in our mailing list, and for our members. So if you want to be in the mail list and receive announcements, then, send us an email. You can follow us on Facebook. And also we have a YouTube channel where we are putting, the recordings of these seminars too. So September, we had Dr. Sag talking to us about COVID. Last month, we had Dr. Siegel talking to us about how to be a better author, right, of scientific manuscripts. And today, we have Dr. Lauren Rast, and she's going to talk to us about modeling optoelectronic metamaterials. So she's the vice president, the current vice president of our Sigma Xi chapter. She is a trailblazer, right? With her BS and PhD in physics from UAB. Even before the seminar, we were talking a little bit that, her first career was actually as a ballet dancer, right? She had scholarships from the Ford Foundation and everything. And her research and teaching interest is physical education, in learning, development of physics course for the online environment, education technologies for in-person and online courses. So we are so happy to have you today, Lauren, to talk to us. And I think that was my...
Thank you so much. All right, I'm going to share my slides now. Okay, so I think I'm good to go.
Yes.
So this is perfect. All right. So this is part of the work that I did during my postdoctoral fellowship at the National Institute of Standards and Technology, and then shortly thereafter, before I returned to UAB, where I'm now an assistant professor in the Department of Physics. So what I want to talk about is metamaterials, a really interesting area of condensed matter physics. So in our common vernacular, sometimes people say that's so meta. So that's often used to mean something in our culture that's self-referential. But in general, the prefix meta means something that's beyond or transcendent. So a metamaterial is a material that's engineered to have properties that are just not naturally found in naturally occurring materials. They can be made of assemblies of elements from composite materials to sometimes metals and plastics. And recently, a lot of progress has been made in the production of two-dimensional materials. and the fabrication of so-called heterostructures, which are composite structures from different 2D materials and combinations of 2D materials with other materials. And these materials can have tailored electronic and also optical properties. So often these metamaterials can be arranged in repeating patterns, and they have feature sizes that are at scales smaller than the wavelength of the phenomena that they influence. So they derive their properties not from the properties of the individual constituent materials, but from their newly designed structure. So these are collective properties of the overall structure that arise. We can think of these as emergent properties of the overall material. So their exact size, shape, orientation, geometry, and arrangement of the materials and the individual materials themselves, and then interactions within the materials give them these smart properties that are capable of doing things like manipulating electromagnetic waves. They can block, absorb, enhance, and bend waves, and really achieve benefits and applications that go beyond what's possible with conventional materials. So I'm going to talk a lot about specifically photonic and optoelectronic metamaterials, which are artificially engineered optical materials. So optical meaning light, electromagnetic waves. And these materials have nanostructures that give them special optical properties. So they're made from at least 2 different materials, usually involving a metal and a dielectric, and they can be periodic. And so the special optical properties don't necessarily arise from band gaps within the materials, although they can, but really from an interaction similar to those with atoms or ions in a solid medium in those types of materials. So we get emergent phenomenon due to geometry within these structures. So photonic metamaterials are described sometimes as homogeneous optical materials, but in a lot of the materials I'll talk about today, they can also be heterogeneous combinations of these materials in layered structures. Okay, so before I get too deep into talking about the metamaterial emergent properties, I kind of need to define some of the important quantities that are, we call them quasi particles, or sometimes collective excitation. So these can be thought of as quantized units that correspond to something with a wave property. If you know about physics, then you know about wave particle duality. So that's what we're thinking about here. And in metamaterials, these different quantized units play an important role in the behavior, the optoelectronic behavior of the metamaterial, but also they interact with one another and produce new phenomena which are of interest. So I'm going to be using these terms a lot. I want to make sure I define them. So a photon is a quantized unit corresponding to the electromagnetic field, right? So light. And then a phonon is going to be a quantized unit of vibration in an atomic lattice. A plasmon is a quantized unit of a plasma oscillation. So a plasma is an electron gas, right? And plasmas can have rapidly oscillating waves of electron density in a conducting medium. And so the plasmon can be thought of as the particle analog of this quantized unit of oscillation, okay? So excitons are also important type of quasi-particle in metamaterials. And those are a bound state of an electron and then an electron hole, which is, a hole is just a place in the structure of the material where there could be an electron and there isn't, okay? So a polariton, when I use that term, that is the coupling. So we have energy and momentum that are coupled. So coupling of a photon with some other quasi particle. So if I say plasmon polariton, that means that a photon is coupled with a plasmon. They're interacting and share energy and momentum. Okay. Okay, so I'm talking about surface plasmons quite a bit. Quantized units of plasma, as I said, plasma oscillation are known as plasmons. And when the real part of the dielectric function in a medium changes sign across some interface, as I've shown in gray here, that's the interface, that boundary there, or a metal and dielectric share this boundary, we get something called a surface plasmon resonant mode. Okay, and these are really important in optoelectronics applications. So these surface plasmons can couple strongly with a wide variety of collective oscillations and quasi particles to form other quasi particles and collective modes. And all of these interesting quasi particle interactions really just allow for a really wide variety of behaviors that are interesting in different areas of optoelectronics. Okay, so for example, the strong optical confinement of plasmons relative to the wavelength of light leads to really intense enhancement of the electromagnetic field locally. So the field enhancement in metallic nanoclusters can actually provide a 10 to the 15th intrinsic enhancement factor of the field, allowing for things like single molecule detection via surface enhanced Raman spectroscopy. So we're talking about really high resolution imaging as one of our important applications for these types of materials. So to carefully define this term of optoelectronics, this is a study and application of electronic devices and systems that source, they can control light, and is considered a field of photonics. So when I'm talking about light, I include not just visible light, but also things like gamma rays, X-rays, infrared often, and visible light, optoelectronic devices. Can do things like electrical to optical transducing. Pressure, in terms of pressure or brightness, converting into an electrical signal or an electrical signal into a photonic signal, vice versa. So they're very useful in these photonic circuits applications. We also look at these materials in terms of quantum computing and applications like that. So one really interesting feature of these materials is that normally when we have an optical component with dimensions near the wavelength of light, we have a problem with diffraction. We say that we are diffraction limited. So diffraction is just the bending of waves around corners and edges. So this diffraction limitation for a lot of conventional optical materials like a lens that you think of means that part of the field signal is rapidly attenuated, and slightly far away you get when the image is reconstructed, you get a really dramatic reduction in the resolution of the image. But because of the confinement of these plasmons to in one dimension, so they move along two-dimensional surface approximately, this diffraction limitation is not so much of an issue. So this has really important applications also in areas like high resolution imaging and detection of small molecules and things like that. So given the enormous electromagnetic field enhancement and unparalleled control over signal propagation, the ability to overcome the diffraction limit that I just mentioned, it's really not surprising that you've seen a lot of growth in this field of plasmonics recently. They found all kinds of applications in spectroscopy, in photonics, biomedicine, telecommunications, as I said, quantum computing. But there is a problem with the practical application of these materials. And so one area that is problematic in terms of practical applications is that they're plagued by losses, so energy losses, including ohmic losses. Surface plasmons also are traveling along, when they're traveling along a metallic surface, they're rapidly damped through a variety of loss pathways. So although it's been determined that these negative index materials that support surface plasmon resonance can be fabricated with low losses, it's clear that these new materials really need careful structural design to ensure that that's the case in device applications. So optical properties of metal nanoparticle systems are really sensitive to geometric configurations of nanoparticles in those systems. Particle size, shape, distribution, dielectric environment really strongly influence the position of the surface plasmon resonance in terms of the energy where the resonance occurs, and also the intensity of these resonance peaks. So for example, when metal nanoparticles are close to one another, interaction of the local electric field of these nanoparticles can lead to really significant changes in the property of the field. And this leads to, for example, additional resonance peaks for the system. So you get extra peaks just by bringing these particles near one another. So traditional metallic nanoparticles, like silver and gold nanoparticles of various shapes and sizes, are still in the pipeline for their full potential for industrial type applications. So the main hindrance towards a more broad application of these materials are these losses that I mentioned before. So in metals, primary plasmon loss mechanisms include scattering, radiative losses, and ohmic losses. And a different loss mechanism will dominate depending on the frequency, nanomaterial size, morphology, and the makeup of these nanoparticle systems. Radiative damping is smaller for these small particles, but even in the small size regime, ohmic losses of energy are still an issue. So plasmonic efficiency can be quantified through the use of parameters such as propagation length, which I'm going to define here on these slides, propagation length and quality factor. Okay. So I want to define first the propagation length term. So the behavior of a plasmon excitation in a medium can be described by the frequency dependent dielectric function of the medium. So when you learn about dielectric properties, if you take your physics 2 course, you often learn of a dielectric constant. Well, actually dielectric functions are frequency dependent. Sometimes they can even be anisotropic, so they vary within the material itself. So the general expression for the dielectric function in a medium is given on this equation 1. And so we have a real and imaginary part of this dielectric function, and losses in a conducting medium due to various mechanisms that we already mentioned are represented by epsilon double prime. The complex in-plane plasmon wave number is given on the page, and we're just going to use that to define this quantity, which is the propagation length of a plasmon. And this is typically defined as the length at which the intensity of the surface plasmon polariton has decayed by a factor of 1/e. Okay, so we can define this quantity, and then we can say some very specific things about which types of materials have longer propagation lengths. And then we'll look at this quality factor as well in just a minute. So another useful parameter for quantifying plasmonic material desirability is the Plasmon oscillation quality factor that I just mentioned a moment ago. So both propagation length and quality factor are determined by damping due to energy loss. Okay. So we have the quality factor Q, which is given by this expression here, shown on the page, where EP is the plasmon energy, plasmon peak energy, and gamma is the full width of the plasmon peak at half its maximum amplitude, so full width, half max. Okay, so plasmon losses and small plasmon losses and longer propagation length are inextricably related to one another, and we want larger L values are really important in things like photonic circuits, waveguides, and photovoltaics. Okay. Okay, so this is a conceptual illustration of this quality factor. And materials in general, with a narrow and intense plasmon resonance peak, that's what we're looking for. Those represent a higher Q factor, okay? So narrow and intense plasmon resonance peak. Okay, so materials with simultaneous large values for L or Q and significant localization of the plasmon are really the supreme goal for most, if not probably all, plasmonics applications. That's what you're trying to tune for. Also, it's desirable sometimes for different applications that we can tune the location of the plasmon resonances themselves. So we're trying to shape the peaks and tune them. So in principle, one way that we can create materials with high Q factors is to mitigate bulk plasmon losses. So really to tune, to favor surface plasmon resonances over bulk plasmon resonances. So the surface plasmon resonances, remember, are confined in one dimension, travel along to the two-dimensional surface. So one way to do this is to mitigate losses through fabrication of really, really thin metallic films. So in this way, makes sense, right? Plasmon resonances couple more strongly to the surface plasmon modes. There isn't much bulk there to couple with, right? So we have a higher surface to volume ratio. So this figure shows this effect. And what we have here in the figure, if you look at this, starting off at 50 nanometer thickness for thin silver film on a silicon substrate. And these are calculated values. I'll talk more about how these calculations were done in just a moment. But the thicknesses go from 50 nanometers with the solid black line all the way down to 4 nanometers with the dotted green line. And if you notice that for all of these, there are two peaks. We have this higher energy peak and a lower energy peak. This isn't the zero loss peak that I'm going to show when I talk a little bit more about spectroscopy. These are surface and bulk peaks. Okay, so one way to couple more strongly, as I said, to these surface modes is just to make your layers thinner and thinner, and you can see kind of a dramatic effect as we go down from 50 nanometers to 4 nanometers for these silver films. So there are issues though. Fabrication of thin uniform metallic films can be really challenging. So thin metallic films tend to form small islands, and they often require like an adhesion layer. for the substrate, and these adhesion layers, as we said, these quasi particles interact strongly with one another, right? So what happens is it changes the optoelectronic properties of the system when you have these adhesion layers. So, and even really thin noble metal films have significant ohmic losses at visible wavelengths. So thin noble metallic layers might be advantageous for low loss plasmonics as part of some kind of a composite structure. Okay. So just to give you an idea about some of the two-dimensional materials that might go into these structures, because hybrid plasmonic materials, which are part of the more general category of metamaterials, might be able to provide the best of both worlds. So they can exhibit longer propagation distances without a reduction in confinement of the plasmon. So we will have lower losses and longer value for L. So they're really a wide variety. This is actually not exhaustive. And probably since I made this list, there are more of these two-dimensional materials where these values have been measured, but this really just shows a list of some two-dimensional materials or quasi-two-dimensional, so bi-layer, tri-layer type materials for plasmonics applications and locations that have either been experimentally measured or calculated. So those are designated in the list there. Okay. So let's see. In recent years, there's been a lot of progress in large-scale fabrication of these monolayer materials and bilayer materials. And then also in terms of isolation of atomically thin layers of two-dimensional and quasi-two-dimensional materials. So it's been a while since we've created monolayer graphene. Yeah, all of this sort of zoo of two-dimensional materials is now available, and people have found ways to more reliably fabricate them with predictable properties. Okay, so we're going to talk about combining those with metallic plasmonic materials like silver. Okay, so here are some 2D materials in the figure. These are the crystal structures for some representative 2D plasmonic materials. So what I have here on top is graphene, and then silicene and germanene have a similar structure. And then we have below there the transition metal dichalcogenides of trigonal coordination. Let's talk about some of these different materials. One of these materials also that has similar structure to graphene is hexagonal boron nitride, similar crystal structure to graphene. And when hexagonal boron nitride is used as a substrate to suspend graphene on, the flat morphology and uniformity, along with the near match in the lattice structure of the two materials, leads to some advantageous electronic transport properties that are really close to a suspended sample of graphene. But this actually kind of preserves for industrial applications some of the features of graphene that sometimes some of the production methods for graphene leave you with a sample that is not ideal and sort of is a compromise between what we would expect for the properties of graphite and pure graphene. And this hexagonal boron nitride substrate, because it flattens the graphene, prevents rippling, and provides properties that are similar to suspended sample, can really be an ideal substrate for graphene. And then silicene and germanene provide electron transport properties similar to graphene, but they also are compatible with our existing ubiquitous silicon-based technologies. So as we make progress forward to more convenient production of these 2D materials, we're paving the road for fabrication of these tailored heterostructures on demand. And we can do things like materials by design for these types of heterostructures. So a 2D crystal-based metamaterial could combine, for example, the sizable band gaps of the transition metal-based 2D materials, which have band gaps that go from indirect to direct and single layers. And they could combine this with the unparalleled strength of graphene, and then this flat morphology of hexagonal boron nitride. So again, these metamaterial structures, these heterostructures, which have layers of different 2D materials within them, combine the advantageous optoelectronic mechanical properties of these materials, and then they also have cooperative effects that are emergent phenomena just of the heterostructure that you wouldn't see for the individual material properties. So rational design of 2D heterostructures really hinges on reliable data on material properties for individual layers, comprehensive databases for these material properties. So this is an area where big data can play an important role. And then also efficient methods for multi-scale calculation of these collective properties for these systems. So also advanced software frameworks for design, optimized design of these materials, and things like model inversion and predictive modeling. We've come a long way in terms of machine learning and artificial intelligence. So those frameworks can play an important role in materials discovery and materials by design. So as we mentioned before, these hybrid plasmonic materials are good candidates for these high Q factor plasmonic materials. So those that contain metal and a combination of a high or low refractive index materials exhibit longer propagation distances. Okay, so this is one way to model these heterostructures. And it works, it's a classical model. And it works within the regime that we tested it for. And I'm going to say a little bit about limitations of this type of a model later on. But this model is very, very efficient. So what I have here is an effective dielectric function for the stratified, so like layered structure, layered heterostructure for a metamaterial. And it's extremely computationally fast. So it really, for a multi-layered structure, this kind of a calculation will run in under a second on a PC. Okay, so this expression was first derived by Lambin, and the idea here really is that we have this specular reflection type, like a mirror reflection type model for a multi-layered structure. And this expression was found for electron energy loss spectroscopy in this reflection geometry. But it's been shown that it applies for electron energy loss spectra for phonons that we discussed earlier, surface plasmon polaritons, and a lot of different quasi particle type collective modes in these multi-layer heterostructures. So the idea is that we have these interacting interfaces in this sandwich structure, and we're able to find the overall dielectric function from this expression. Okay, so the dielectric function of an individual layer thickness is what's shown there. So the thickness di, and then this is given by, if I find the next expression here. Let's see. Yes, we have the composite function there. I'm going to show how we connect this in just a minute to the overall electron energy loss spectra, but I want to show first how we construct, if you look at this, we have A1 and B1. Those are values, those are expressions for individual layers. So we're looking at inputting the dielectric function for an individual layer and the thickness for that layer into an expression. And so we need material properties for the components of these heterostructures. So where do we get the material properties? And you can do this in a variety of ways, a really flexible way of calculating the overall, the effective dielectric function. For silver and for the other metallic materials, we used in our paper that we wrote on this with two of my collaborators, we used empirical values from the literature. So Johnson and Christie have a paper that is very widely used for empirical values of dielectric functions for metals and thin metals. But for the 2D materials, what was used is density functional theory. So density functional theory is a quantum mechanical method that's widely used in physics and chemistry and condensed matter physics, material science to find the electronic structure for atoms, molecules, and also for different types of thin materials, but it can be computationally intensive. So people are now, as computing power goes up and issues with computationally intensive distributed things that need to be done on distributed computing becomes less of an issue. People are more able to use DFT for the entire layered structure, but for the modeling the continuum, so bulk properties of structures that have these really small nanoscale features, still kind of a challenge. So that's why we would want an algorithm like this, possibly for materials by design. But for our 2D materials, that's what I used. I used density functional theory to model the optical properties and to find the dielectric function for the individual layers. Okay. So there are a lot of these DFT codes out there. I liked this one because it has a time-dependent, can do time-dependent calculations, and you can connect it to something called the Bethe-Salpeter equation, which is good for calculating spectral properties of materials. Okay, so the final expression for the electron energy loss function, which is going to create our model spectra, is given there. So we just take the composite dielectric function and then calculate that. So let's see. Yeah, once the individual dielectric functions were obtained from the calculations, then we combine that with the empirical data and put this into the composite dielectric function and then calculated the spectra. So I'll show you the model spectra here. So, but just quickly, so we're on the same page with what, in case we don't have all spectroscopists in our audience. So spectroscopy is the study of spectra produced when a material interacts with and also emits electromagnetic radiation. So these techniques, the sample is exposed to a beam of electrons with a narrow range of kinetic energies. And some of the electrons will undergo inelastic scattering during this. So they lose energy and have their path slightly and randomly deflected during these collisions. So the amount of energy loss can then be measured by an electron spectrometer. And then we interpret it in terms of the data that you see here, which is in terms of what caused the energy loss. So we have devices like a transmission electron microscope, and this that works with electron energy loss spectroscopy, and it can provide structural and chemical information about different samples. And we can even go down to, with this type of measurement, atomic resolution of a sample. Okay, so we have an idealized generic spectra here. On the left, that's a zero loss for elastic collisions peak. That's not going to be included in the model spectra, but we have a plasmon resonance there, and that looks like a bulk plasmon resonance. And so we have a broad peak that's shown in this model spectra. So. Okay, so let's look at some of these results. So in this example here, what I have modeled is a graphene layered structure. So we have a semi-infinite silicon bottom layer and then a silicon dioxide layer above that, which often happens during the fabrication process. You get a thin layer of silicon dioxide. And then a 34 nanometer silver layer, 34 nanometers, because that's the nominal size from the literature. And then a single graphene top layer coating, and then above that, vacuum. In the results for the loss function over here, we have a dotted line where there's the semi-infinite silicon bottom layer, SiO2 layer, silver, and then vacuum. Okay, and then when we add the graphene layer on top, that's the solid line there. So what we notice is a behavior that bears physical similarity to something called the Begrenzungs effect. Begrenzung is just a word that means boundary. So this effect arises due to a reduction in the degree of freedom for the plasmonic excitation. So when we confine a plasmon in one dimension so that it's moving along the two-dimensional surface, what we notice is that, you look at the B, there is the surface peak. That isn't changed, but we reduce coupling to the bulk peak on the right there. Okay, so we have in this type of structure, I'm going to show the spectral results for this type of system, adding different layers of 2D materials, so starting with graphene. Okay. So we have a multi-layer structure with graphene top layers, various numbers of layers, some intermediate layer that's made out of a noble metal, and then a semiconducting substrate below. So we'll look at silicon dioxide and also hexagonal boron nitride spectra. Yeah. So for a few layers of graphene, the lower peak, and that one's near about 2.6 EVs, is really virtually unchanged. And then you can see that, that as you add layers, so we're starting with, on top there, that's for silver as an intermediate layer, and then a silicon dioxide substrate. So as we go from, let's see, zero layers of graphene, the solid line, and then a single line with long dashes, and then 3 layers for the intermediate length dashes, and then up to 10 layers for the short dashes, and then the dotted line corresponds to 20 layers of graphene. We initially, what happens is we reduce coupling to the bulk mode, and the surface mode is virtually unchanged. But then what you notice, after around 3 layers of graphene, you get this broadening of the bulk peak. And what that corresponds to is what you would expect your spectra to look like if you had a deposit of graphite on top. Okay. So there's really kind of a happy medium there, where a few layers of graphene can help mitigate losses and enhanced coupling to the surface modes. And then beyond that, you get probably enhanced losses and dampening of peaks. Okay, so this shows graphene films for varying numbers of layers on a 34 nanometer silver film and a single layer hexagonal boron nitride substrate. So without graphene is the solid line, and then single layer of graphene is the long dashes, 3 layers is 10 is the short dashes, and 20 is the dotted line. Okay. Because hexagonal boron nitride is very strongly insulating, the substrate material reduces bulk losses, and it strengthens confinement to the surface modes due to reduced scattering within the material, so confining our plasmons further. Okay. And again, we notice that once we start to have a lot of these layers of graphene, we start to get something that looks more like a graphite coating on top of the broadening of that peak. Okay. So here we have electron energy loss functions for silver, just to compare silver films of various thicknesses. So showing where we go from 50 nanometers down to 4, where we have the dotted line. And then in B, 3 layers of graphene on silver with a monolayer hexagonal boron nitride substrate. So it turns out that the spectral profile that we see with hexagonal boron nitride is really, really similar to what we would find in the literature for a suspended sample of graphene. So like there's no substrate there, except that it helps the graphene sample stay flat and preserve the electron transport properties of graphene. Okay, so I want to look at some other materials, silicene and germanene. Silicene and germanene are 2-dimensional allotropes of silicon and then also germanium. And these materials possess transport properties really similar to graphene. But as we said before, they're compatible with silicon technology, silicon-based technology. So the reactivity of these materials mean that they're more challenging to fabricate than graphene. And so some of these results that I'm going to show for these systems, and just because of time, I think I'm going to skip ahead so I can show some fun examples at the end. But it turns out that some of the results we got here can help us to determine how many layers of silicene and germanene we've deposited. So this is just the calculation for the dielectric function of silicene and germanene. And so in these spectra, we get a marked difference in spectra with 3 layers or more in broadening of the peaks. So this could help in experimentally verifying that you have only a few layers of these materials on top of a metallic substrate in experimental conditions. So I'm going to move on to some of these fun examples because I'm short on time and want to make sure that I get some of these like future directions and things that have been done really, really recently in the time that we have left. So let's see here. So what I want to talk about are strain-induced charge distortions. So this shows buckling of graphene, which we often see in fabricated samples. And the implications of this are really interesting. So strain in graphene, where the lattice is distorted and buckled in this way, can lead to something called a pseudo-magnetic field that behaves like a magnetic field. And with these pseudo-magnetic fields, the distribution of the field depends on the strain pattern. So it's something that's kind of tunable. And recently, I think there have been some papers that have come out where people have modeled and done measurements with materials like this. I saw one that said there was a 300 Tesla pseudo magnetic field that was measured in graphene nanobubbles. So if you compare that, you know, that's several hundred times more than what you would see in an MRI machine. It's an enormous value for a magnetic field. Okay. These are anti-dot arrays. And so these are really cool structures for when we have dots where we've removed part of the lattice. And these are known to have really strong optical resonances in the microwave and terahertz regions. And they also have tunable plasmon resonances based on the way that you fabricate these structures. So electrons moving through a periodic lattice structure like this, they have a field, they develop a quantized energy spectrum that has degenerate Landau energy levels. And one thing that is really interesting about these is that you have, when you subject them to both a magnetic field and an electrostatic potential, these 2D systems have self-similar recursive energy patterns, so like a fractal energy pattern. So really, really interesting electronic structure properties for these types of materials. And this is another really interesting one in the area of spintronics. So when a layer of graphene is dropped on top of another layer of graphene, or sometimes even hexagonal boron nitride, and then rotated what we call the magic angle, then we have really special properties for the band structure of these materials, and they can even become superconductive. So why does this happen? It has to do with these moire patterns that are created. So this is the true metamaterial in the true sense. We have a pattern that occurs on a larger scale, and we have a different overall kind of lattice structure that comes from the collective layers in these materials. So we have a lot of interesting tunable properties for these materials, and we call this area twistronics. Okay. I think this is going to be my last, I'll wrap up with this. So it's been possible for more than a decade to make arrays of metal nanoparticles of controllable size and shape. And we can really now look at varying particle shape and interparticle distance to control absorption spectra for these types of materials. So adjusting the shape of these materials. And then if we dope graphene with these adjustable plasmonic materials, then we can create an extremely enhanced electromagnetic response with tunable optoelectronic properties. So this is important in the area of ultra-fast communications and things like biosensing, so determining different molecules, for example, that might need to be detected on the atomic scale. And then lastly, I mentioned this already, but we have a new paradigm created by artificial intelligence and big data, where there's a lot of opportunity to do materials by design for these types of structures. So machine learning can help us to find different metamaterials that we would not have been able to predict in the past. So I'm going to wrap it up with that. I just want to say thank you for this opportunity to speak at Sigma Xi.
All right, so we do have one question, and if anybody has any questions, please put in the chat box. So we have a question here. So are you dealing with natural, and this is from James, I'm sorry, I need to learn how to be a better host of those.
Sorry.
So a question from James is, are you dealing with natural occurring graphene as occurs in Alabama, or is it a created processed material?
So mainly talking about created processed materials, but it could be naturally occurring graphene. There have been a lot of, especially since we've done this work, there have been a lot of advances in terms of fabrication of graphene. So for a while, you know, the initial way that you would get graphene would be from graphite samples, right? We had this, when graphene was discovered, just removing layers until you wound up with a single layer of graphene, right? And then we had chemical vapor deposition for producing graphene. And there were a lot of problems with that for a while because you would kind of get, like I said before, the properties kind of intermediate between graphite and graphene. And so a lot of the, some of the properties that are really exciting about graphene, like really high rates of electron transport, things that make it exciting for circuits and for like solar cell applications, didn't really work from these fabricated samples. But now that the technology has kind of come into its own, where people are able to produce more idealized graphene sample. So mainly talking about graphene produced in the lab. Of course, a lot of this would apply to, you know, graphene that could be found in nature as well. Yeah, but the combinations, like these layered structures, that's not really found in nature. You don't find a nice two-dimensional sheet of graphene on top of a sheet of hexagonal boron nitride, just out there in nature. Yeah.
All right. So, you know, since we are Sigma Xi and we want to encourage people, you know, to go into science, I was just curious what drove your interest in physics and modeling and physics education. What is the importance of physics education?
Oh my gosh, I'm so glad you asked that. Yeah. So I was. You said before, this is my second career. I was in the arts as a young person, but I was always curious about the natural world and about how things worked. And I was also always very interested in mathematics and trying to understand nature. And so, you know, I went through a long period where I just wanted to find out. I didn't even think of it when I was, you know, a teenager as this is a fabulous career that I could have in law. I thought of it as I just really want to understand. And also being a computer nerd from a very young age, that kind of led me to computational physics. And I had a really awesome opportunity when I was doing my postdoc to do a lot of mentoring with high school and undergraduate students. And I really found, I had always taught when I was in graduate school, and even undergraduate, I had a chance to do a lot of like helping with teaching. I had some really good mentors there, but I kind of found my way back to the area of education as a real passion, mentoring students and teaching them how to do these same things that I was passionate about. So yeah, I mean, I think that really you can learn anything if you can break it down into small enough pieces, right? And so I think that education and education research, really, it's surprising people with what they can do, and seeing that you can understand things that you wouldn't have thought you could understand. You can do things that you wouldn't have thought you could do. If you really, students, it makes a huge difference if you have somebody who kind of believes in you and sees maybe what you don't see at that point in time. You can kind of break it down so that you push it a little farther. Yeah, so it's a career that's been really good to me. Yeah.
Lauren, this is Maggie. I'm sorry, my camera's a little goofy today. No, and sorry that I'm late to your show, but enjoyed it. Got the bulk of it. So I was playing a little bit of catch up there for a while, trying to get in with all the terminology. But I'm curious if you have one dream application for your metamaterial, you know, the heterostructures. If there's one thing that you really want to do.
Solar cells. I really love the idea of graphene-based solar cells. So, or any two-dimensional based solar cell applications, because I think they have really, really incredible potential in terms of renewable energy sources. You can get a high Q factor, right, with the visible spectrum and create energy applications like that. I think that's something that can make a difference in the world. Yeah, I mean, they're useful in so many areas, but that's my favorite one.
Understandably, thank you.
Thank you.
Thank you, Dr. Rast. Thank you, everybody. And we'll be back in January with our series. Thank you.
Awesome. Thanks, everybody. See you later.
Take care. Happy holidays.